Hey everyone. So today we'll be revising backtracking from Leetcode list. Um, yeah. So let's get started. Let's see the first question. And today I was trying to solve the uh, meetings room 3, but unfortunately I was not able to solve that question. I will increase the font size. Um, and make this a bit larger. Yeah. So the question is, given an integer array nums of unique elements, return all possible subsets, the power set. Okay. The solution set must not contain duplicate subsets. Return the solution in any order. Got it. Okay. So, given an integer array nums of unique elements, return all possible subsets. The solution set must not contain duplicate subset. Return the subset in any order. Got it. So we need so when we are backtracking, basically, so yeah, like we have to do a recursive search on every element. However, see one has 1 2, one has 1 3, one has 1 2 3. So it's just like I take one, I leave one at every stage, and I don't want to repeat whatever number, like the combination that I'm generating, right? So let's go to our visualizing board. Don't want to waste a lot of time here, but yeah. Okay. Um, Delete everything, go back here and take this guy, and yeah, we have subsets 1, 2, and 3. So all we can do is, for everything, we can take either the empty subset, or let's not worry about the empty subset for now, and let's do this one. I can either take 1 or not take 1. If I take 1, then the next would be I can either take 2. So this would be 1 2, or else I can take 1 3, skipping this one. I can take, sorry, what's this? I can take 1 2 3, or I can just have 1 2. I can have 1 3, and this cannot go any further, right? So next I can just take 2, then okay, wait a minute, I might have done something wrong here. So I can just take 1, keep 1, and take 1 2, keep 1. Okay, keep 1. But the confusion here is, how will I just keep 1 and keep moving forward? How will I do that? Like, what would be my base case for stopping? Can I can I just take a hint, like what's basically going on here? Okay, 1 2 3. So I take result. My current is this. I take DFS to include nums index. So to include nums index and to not include nums index. Current. Okay, I didn't think about this. So so what will happen here? Let's do this in this case. So we have 1. So what we are doing is we are having a result and a current, and we are, as soon as our index goes above nums dot length -1, we push everything into result. Whatever the current we have, we push it, okay, and return. So how is that working? We are having current, we are pushing it, and current dot pop. So we are sending DFS index +1 and DFS index +2. Okay, +1, sorry, +1, index +1. So we have this guy. Sorry for my handwriting, but we have 1 2 3. So what we'll do is, our index is clean at the moment. So we'll do add 1, Then so we pushed 1, then we go ahead, we push 2, uh, push 2 onto this, so 1 and 2. So here index was 0, here index was 1, so here index would be 2. We push 3, 1, 2, 3 is gone. And then, and at index 4, we just add this guy to our results. So I'll make result here, or where should I do it? The screen is getting smaller. So I'll add 1, 2, 3. Okay. So we return from here, return. Okay. And then, so we have traversed till this point of time. So we return back, and then this guy, goes with 1 and 2, just 1 and 2. But index has reached 4, so we add this to 1 and 2. Okay, then we return. Then this whole function returns back to this place. Then we send 2, but we just send 1 here. And then this one guy takes in 3, 1, 3 is sent, and this send 4, then returns. So 1, 3 is also added. Okay. Then this guy returns, and then we have without 3, right? We without 3. So no, it goes back here, and then just one is sent, and then return. Sorry. 1 is returned, and then this guy returns, this whole function's return. Then we kind of pop our 1, and just an empty array is returned, and we add 4. So yeah, I'll just write rest of the stuff here, and empty is added. Then this guy returns back. Then this guy has 1, so for 1 it sends just 2, so 2 it takes so yeah, we have processed everything from here. So what I'll do is I'll just cut this out and move it down somewhere here. Okay, so that it doesn't look messy. And let's do this one. So 2 is there. We increment the count 2. So 2, 3, and we increment the we increment the count, which is 3. Oh, okay. 3. Basically, this will be when it goes to 3. We cannot push anything right at that point of time. So Yeah, at this point, okay, I might have done something wrong, but yeah, at this point, our we can just return back. So I guess this 2 3 is added, 2 3 is added to the answer. Then once this is returned, we don't. Why is this happening? Yeah, we don't add 3. We just add 2, keep it 2, and then it is returned. So 2 is added, and it returns back. Then this guy returns back. So 2, so 2 3 is added. Gotcha, gotcha. So everything will be added at a later point, and we'll have our um, all the subsets that we wanted. We'll have them. So what basically was happening is let result is equal to an empty um, let current is equal to empty. So what we are doing is return result, but before returning result we need to run DFS on 0. Then function DFS index, if index is greater than nums dot length minus 1, what we do is result dot push whatever there is in current, we push it, and then we simply return. And what we do is every time for current dot push nums of index, then DFS index plus 1, and current dot pop DFS index plus 1. Okay, so yeah, uh, if you see 1 2 3, 1 2 1 3 1 2 2 3, and lastly empty was there. Yeah, so somewhere, so see 1 2 3 1 2 1 3 1, we shouldn't have got this. Instead 2 3 2, and then 3, and then the end 1. But yeah, it is what it is. So it was not intuitive, but okay, never mind. I'll work on this, and we'll get better. Okay. But wasn't there a chance of duplicates? I'm just wondering, like, isn't there a chance of getting a duplicate at any time? I guess there won't be, but coming up with this solution is pretty difficult. Kudos to those who can come up with a solution, but yeah, let's do one thing. Um, let's read through this solution and hopefully we can understand better what's going on. Le- So there is some mathematics, permutation and combinations are going on here. So let us first review the problem of permutation, combination, and subsets. Since they are quite similar to each other and there are some common strategies to solve them, first, their solution space is often quite large. Permutation is uh, n factorial and combinations is c raised to k. Subsets 2 raised to n, yeah, since each element could be absent or present. Got it. Given the exponential solution space, it is tricky to ensure that the generated solution are complete and non-redundant. Complete and non-redundant. Okay. It is essential to have a clear and easy to reason strategy. There are generally three strategies to do it: recursion, backtracking, lexicography generation based on the mapping between binary bit mask and the corresponding permutation combination subsets. As one would see later, the third method could be a good candidate for the interview because it simplifies the problem to generation of binary number. Therefore, it is easy to implement and verify that no solution is missing. Besides, as a bonus, it generates lexicographically sorted output for the sorted input. Cascading approach first. Intuition. Let's start from empty subset in the in output list. At each step, one takes one integer into consideration and generate new subsets from the existing ones. Start from an empty subset, put take one into consideration and add. Okay, take two into consideration and add new subsets by updating existing ones. Output. Take three into consideration and add new subsets by updating existing ones. Output. One, two, one, two, one, two, one, two, three, 1, 3, 2, 3, 1, 2, 3. Okay. For let nums, new subsets, new array. For current output, subsets dot add n into 2 raised to n. So we created a subset for all the nums. For current, what is uh, output? Okay, output. So new subsets dot add new array list current and add num. Backtracking power set is all possible combination of all possible length from 0 to n. Given the definition, the problem can also be interpreted as finding the power set from a sequence. So this time let us loop over the length of combination rather than the candidate number and generate all combinations for a given length with the help of backtracking technique. 1, 2, 3 iterate over all possible lengths from 0 to n. all subsets of length 0, 1, 2, 3. Backtracking is an algorithm for finding all solutions by exploring all potential candidates. If the solution candidate turns not to be a not turns to be not a solution, or at least not the last one, backtracking algorithm discards it by making some changes on the previous steps. That is backtrack and then try again. Backtracking generates all possible subsets of length 2. Yeah. Use the next element nums1 and nums2 to complete the subset. Okay, so both of them are right. Both of them are right, but I'll I'll stick to what I've learned and uh, not this. N into 10 raised to n into 10 raised to n to generate all subsets, then copy them into output list. So for 1, okay, I might have seen um, because we copy the list of length at most n at the end of every subset, and there are 2 raised to n subsets in total. We are iterating through the length of the list and finding all combination of each length. Okay, let's see what Neetcode has to say, and probably we can come up with a solution by our own in the next one.
Hey everyone, welcome back, and let's write some more Neetcode today. So today let's solve the problem subsets. So we are given an integer array nums, and all we need to do is return every single possible subset that we could create from the input nums. And we do not want to include any duplicate subsets. So what is a subset? Well, let's say we have 1, 2, 3 as our input. One subset, of course, would be 1, right, by itself. Another subset would be 2 by itself. We could do 1, 2 together. Now, what happens if we do 2, 1, right? We just swap the order. Does that count as a different subset, or is that the same as this subset? Well, they're the exact same. We don't care about the order. This is not a permutation. This is a subset. So it's not a permutation, it's a subset. So we do not want to include duplicates, and this counts as a duplicate. We're not going to include it. And 3 is another subset. 1, 3, 2, 3, 1, 2, 3. The original input is technically also a subset. And we also don't want to forget the empty subset. So no matter what we're given, an empty subset is technically a subset of this as well. So if we want to create all the subsets from this input, we have a choice for every single element. So for this 1, we have a choice of include the 1 in our subset or not include the 1, so we get an empty subset, right? So we have that choice, and we have that choice for every single input element. So in total, we have 2 choices here, 2 choices here, and 2 choices here. So this is going to be 8, or in other words, 2 to the power of n, where n is the size of our input. Right, so this is the number of subsets, and we don't want the number of subsets, we actually want the subsets themselves. So how long could a subset be, right? Well, we could have a subset 1, 2, 3, right, the size of our input. We could also have subsets that are smaller, right, like 1, 2, maybe 2, 3. So as you can tell, this is not going to be an efficient problem to solve. We have this many subsets, and each subset could be up to length n. So the worst case time complexity of this problem is going to be n times 2 to the n, regardless of how efficient we make it. Because given the constraints of this problem, we don't want the number of subsets, we want the subsets themselves. We have to make it inefficient. So with this in mind, we can just jump straight into backtracking, which is the brute force way of solving this problem, but it's also pretty much the most efficient way. So like I said, for each of these elements, we have a choice. So I'm going to draw the decision tree. So first we can choose to add 1 or not add 1, and that will give us 2 subsets, 1 subset with just 1 and 1 empty subset. So along this path, we can decide now, do we want to add 2 or not add 2? So with one decision, we will add 2, and the other decision, we won't add 2. So we'll get 1, 2 as one subset, and the other subset will just be 1 by itself. And we can actually repeat that on the right subtree for 2. So we can decide to add 2 to this empty subset, or we can decide to not add 2 to the empty subset, in which case we'll get a subset with 2 by itself, or we'll get the empty subset again, right? This is where we're just not adding anything. And lastly, we can decide whether we want to add this 3 or not. So if we add the 3 to this subset, we'll get 1, 2, 3. If we don't add the 3, then we will remain as 1, 2. And we can repeat that decision over here. And that's basically what I'm going to do now, right? Repeat that decision for every single one of our, like you can call them nodes or you can call them leaf nodes. That's just what we're doing. So if I add the 3 here, we'll have a 1, 3. If I do not add the 3 here, we'll have the 1 by itself. So you can kind of see these are 4 unique subsets, right? Now let's build the rest of the 4 from over here. So I have the choice, do I add 3 or do I not add 3 to this subset? If I do, I will get 2, 3. If I don't, I will have 2 by itself. And you can see these 2 subsets are different from the subsets over here. These are still unique. And lastly, we can choose to add 3 to the empty subset, or we can choose not to add 3 to the empty subset, in which case we'll get a single empty subset. Now you can see we keep multiplying by 2, right? So here we had 1. We multiply by 2. Now we have 2 subsets over here, right? We go down again, we multiply by 2. Now we have 4 subsets over here, right? Then we go down one more time, multiply by 2. We have 8 subsets, and they're all unique. This is our result. This is what we're building with this problem. This is backtracking. Now, if you want to know how to do this backtracking solution in code, let me show you right now. So let's do this with backtracking. So we're going to have a result list, which we're going to add these subsets to the decision. So if it's greater than each subset, I'm going to have an array, and the base case we know this subset, and that's going to be the take the subset we had an empty subset and we had 1, that's the same as if we returned 1 and the empty subset, right? Like the order that we put the subsets in doesn't actually matter. But again, I hope this was helpful. If you enjoyed, please like and subscribe. It supports the channel. We keep
So he explained truly beautifully. Uh, I wish I can also explain like that, but wishing is not all that we want. We'll actually try to, at least if we can explain as good as him, that will be extremely helpful in explaining our thought process to interviewer as well. Even if we can do 1% of, at least 30-40% as good as him. So yeah, let's try to do this. So we have 1 2 3. Okay, so for every node what we are doing, we are taking a decision to take it or not. So we start from 0, right? We decide to take this 1, then we decide not to take this 1. Okay, and then for 1 we decide to take the 2 when index increases, then and 0 1 2, and when index is 1 we not to decide not to take 1. But first let's traverse this side. We do 2, and once we reach 2 we decide to take this 1 2 3. Okay, so that's it, and we return back from here. So I'll indicate red when we are returning back, and so here when our 2 is there, then we not decide to take 3. Okay, and then here we return back. So return back to this guy, then will not take 2, and here we'll reach 2, and then this would be will take 3, and here we won't take 3, so 1. And then yeah, we return from here, and then we went here, sorry. So then what we do is we keep on returning back and come to this guy. So here when we, okay, how does he create his tree so perfect? So 0 I have an empty, then for 1 I do it, I add 2 and decide not to add anything. For 2 I add 2 3, then return from here, and then I decide not to add anything 2. Then I again return from here, then we return from here, then we come to this guy, and then we decide to add 3 and not to add 3. Okay, so that's how we got this one, and yeah, basically this is the answer, this guy. So at every stage we are taking 1, 4, 2 4 8, right? So n for copying, n into 2 raised to n time complexity. Okay, and space would be n because at a particular time we would be only accessing this this tree, and then once this is done, uh, we so is there a back button? Okay, there is no back button, but yeah, and then once we traverse this, then then we traverse this. So at any point we'll be having n, which is the height of tree. Okay, so once this is done, we'll be traversing this part. Once that is done, we will traversing this part. Once that is done, we'll be traversing this part. Once that is done, we'll be traversing this part. Yeah, hope this idea is clear. So that's why 2 raised to that's why our memory time complexity would be um, O of n, because will be our stack will be always be the height of. So this is time complexity, and this is space complexity, SCTC. Okay, cool. So we'll take 5 minutes break and we'll come back. It shouldn't have taken more time, but eventually we coded it up and saw what is the best solution, so that our foundation goes stronger as we move forward to the next questions. So let's take that break, and before taking that break, I just want to see how many companies like to ask. Oh, a lot of companies like to ask this question, so this is pretty important question for us. So star market, and let's move on to the next one in like 5 to 10 minutes. Okay,